ever since I was a kid, I've had an interest in astronomy, like quite a few people have. And I've got a photograph here of when I was about 12 years old at school. This is our astronomy club at school. And I am this person over on the left here. You might have heard of this person, the tall fellow at the back there. That's Douglas Adams, who wrote The Hitchhiker's Guide to the Galaxy, who was in my class and in my astronomy group at the time. He's had a more illustrious life than I have. But unfortunately, he's only lasted 48 years and I'm still going at 72, so I've got that to be grateful for. I've taught at Canterbury since 2004, Canterbury College in Logan. And I just do a little bit of lead teaching now because I'm getting fairly old. But about 2010, I decided to start an astronomy club there to see if that would work. And I've spent 2 weeks advertising the upcoming event in the newsletters, notice boards, etc. And we met on a Friday afternoon after school, and I had a grand turn up of 2 students. And one of them told me that there was a girl, Taylor, and a boy, Jacob. Jacob told me that next week he had soccer training starting, so he couldn't come anymore after that week. So I suggested to Taylor, well, maybe we just give this a miss. And she said, no, I'll come. And so she came back each week and brought a few friends with her. And after a few weeks, we had a small group, and we decorated a room in the library with a bit of astronomical stuff. And we continued till the end of that year, but the next year I decided that I might take a different approach to recruiting. And we decided that we'd have a bit of a Star Wars theme as well as the astronomy, because we thought that a few people might be interested in that. And the next year, Taylor and I went into classrooms dressed as Emperor Palpatine and Darth Vader, and we spoke to the students about the club, and at our first meeting we had a good turnout. So that worked a lot better. And during the year we had stargazing evenings, we had trips to the planetarium, we had family nights where we invite parents and do a bit of a performance for them. And we met for an hour and a half after school every Friday afternoon, which is not the ideal time that students want to stay at school, but we still had a good turnout. And by 2013, when I resigned from full-time work, we had over 100 members in the club, so it was a great success. Unfortunately, it's not running now because it's sort of pretty much petered out after I finished there. But one of the things, what we did in those 1.5 hour meetings, half an hour of it was running through a slideshow to teach them astronomy. And I made about 50 different slideshows on different topics, and what I'm going to do today is run you through one of those slideshows, an introductory one which I would have used sort of at the beginning of the year. Now I just need to put these on, see what I'm doing. Okay. Shall we have those lights off as well? Because that might make it a bit easier.
Or just turn them off.
Oh, they're on permanently, are they? Oh, not tomorrow. Okay. Hopefully you can see that okay. This slideshow is called The Dramatic Universe. If I stand over here and talk like this, can you still hear me?
Yes.
Okay, that's good. So I won't feel sort of tied to the microphone in that case. Okay, most people don't realise that the dinosaurs actually lived on the other side, on the other side of the galaxy. Well, it'd be handy if you realise that. No, most people don't. The Earth's rotation causes most of humanity to move around it at supersonic speed. The speed of sound is about 1,100 kilometres an hour, and we go around it about, in Australia, at about 1,500 kilometres per hour. But of course we're not travelling supersonically because the air's coming with us at the same speed that we're moving. And so standing on Earth, that point you can see at the centre of the circles there is the point in the sky directly above the South Pole. And as the Earth goes round, do I need that? Yes. Oh, okay. Okay. As the Earth goes round, If you're standing at the South Pole, you see the stars all go around in the opposite direction, and that's a time-lapse photograph, not taken at the South Pole, otherwise the centre would be directly overhead, but taken somewhere maybe in Australia. Okay, and the Earth goes around the Sun even faster than 1,600 kilometres now, about 70 times as fast, or about 30 kilometres per second. And it goes around the galaxy 70 times faster than that, about 2,000 kilometres per second. Even at that speed, it takes about 250 million years to go around the galaxy once. Now, the dinosaurs lived 125 million years ago, when the Earth was round the other side of the galaxy. So that's where the dinosaurs lived. So hopefully that makes a little bit of sense. Andromeda is a similar galaxy to the Milky Way. Our galaxy is the Milky Way. It's similar, but it's bigger. You can actually see it, the sort of bright bit in the centre, just with the naked eye if you're in the northern hemisphere. You can't see it very well from here, though. One thing I meant to say before I got going was that these slideshows are designed to be about half an hour if nobody asks a question. We've got about 45 minutes, so feel free to ask questions, interrupt, just give me a wave or just call out, and I'm happy to ask questions along the way. If nobody does, we'll finish a bit early. It's more interesting if we get a few questions along the way. Okay, Andromeda is similar to our Milky Way galaxy, but it's bigger, probably about 1.5 times as big, and it's moving very fast, straight towards us. And it's going to collide with us in about 5 billion years. But we don't need to worry, even though between them the two galaxies contain around 1 trillion stars. The spaces between the stars are so huge that it's unlikely that there will be even a single collision between stars. The gravitational attraction between the stars, however, will cause them to change direction. So, stars in both galaxies at the moment are travelling in nice, neat circles. They're both spiral galaxies. As they come together, though, the gravitational force is going to get them all to go off in random directions. And so we'll have one combined galaxy of stars going everywhere. And it will, the two galaxies won't just pass through each other. The two spiral galaxies will combine to form one elliptical galaxy. Like that one, where the stars, instead of all going round in the same direction, they're all going all over the place, which is why the thing looks like a smudge rather than a disk. Another reason not to worry is that by then our sun would have expanded into a red giant and swallowed the Earth anyway. When the Earth was young, the Moon was only 1/15 as far away as it is now. It's very, very close. So it was 15 times as wide in the sky, something like that, and more than 200 times as bright. And it all being very close, it orbited the Earth in 27 hours. And there would have been a total eclipse of the Sun and a total eclipse of the Moon on each orbit, because the Moon sort of took up so much of the sky that it would obscure the Sun every time it went past, and it would have been obscured by the Earth as it went around the other side. In those days, the Earth rotated in 6 hours as well.
How much younger were we?
The Earth was formed 4.5 billion years ago, and so that was sort of, the Moon was formed pretty much at the same time, just shortly after the Earth. The Moon was actually formed, they think, by another planet about the size of Mars crashing into the Earth, throwing a lot of the mantle of the Earth into space, and that then accumulated in orbit around the Earth and formed the Moon. And that was about 4.5 billion years ago. So in the first 500 million years or so of the Earth's existence, that would have been the case. The Moon has gradually moved further away from the Earth, and the Earth has gradually slowed down since. When the Earth was young, the Sun was cooler too. It's getting hotter by about 7% every billion years. 4 billion years ago, 500 million years after it was formed, the Earth would have been entirely frozen because the sun wasn't as warm then, if it wasn't for a methane-rich atmosphere, which produces a very strong greenhouse effect. Methane is a very strong greenhouse gas, much stronger than carbon dioxide. We don't have a lot of it in the atmosphere at the moment, but we had a lot then. 3 billion years ago, bacteria developed. Bacteria developed photosynthesis. There were bacteria around well before that, but they developed photosynthesis, which produced oxygen. And the oxygen reacted with dissolved iron in the sea. So the sea was full of dissolved iron, but not being there any oxygen, it stayed in solution. And it reacted with the dissolved iron, causing it to precipitate onto the sea floor, and it produced the banded iron formations which provide most of our iron ore today, like all the iron ore in the Kimberleys is all banded iron formations. It's an alternation of the red bands are iron oxide and the white and grey bands are silica. Eventually, more oxygen was produced than could be absorbed by the iron, and it started to accumulate in the sea and in the atmosphere. Life on Earth was anaerobic, which means that it didn't use oxygen for its metabolism. In fact, the oxygen poisoned it, leading to the oxygen catastrophe. Almost all living things died. It was a bit like being asphyxiated by your own flatulence. Only those few things that could handle the oxygen survived. Some bacteria evolved that could actually use oxygen for their metabolism, and these eventually evolved into us. And so catastrophes aren't always bad in the long run. Not so good in the short run often. The other thing the oxygen did was oxidize the methane. And methane combines with oxygen to produce carbon dioxide and water. And this reduced the greenhouse effect and cooled the Earth, because carbon dioxide is only about 1/30th as effective as a greenhouse gas as methane is. And so the greenhouse effect was reduced, the Earth cooled. A bit over 2 billion years ago, there was a snowball Earth event. The entire Earth was frozen right to the equator for over 100 million years. Not much happened during that time, but bacteria still survived in the water underneath. Of course, the sun will continue to get hotter. A couple of billion years from now, the heat will have caused the oceans to evaporate away into space. Another 3 billion years after that, and the sun will become a red giant, and the rocky surface of the Earth will melt. If it gets included in the sun, it might even evaporate. We don't quite know exactly how far the sun will come out as a red giant. The sun will spend about 1 billion years as a red giant, then shrink down to a white dwarf, about the same size as the Earth, 1/1,000,000th its present size. The sun is presently about 100 times the diameter of the Earth, and therefore 1,000,000 times its volume. And so it will shrink down to about 1/1,000,000th of the volume that it is now. It will still have most of its present mass, so it will be very dense. 1 teaspoonful of a white dwarf, if you can scoop it up, weighs about 5 tons. About the size of a small truck. White dwarfs don't produce any energy, so they eventually cool down and become black dwarfs. But this takes a long time. Tens of billions of years, longer than the universe has existed to date. The universe is thought to have started 13.8 billion years ago, so the Earth is about 1/3 the age of the universe. So there are no black dwarfs yet. A white dwarf is mostly carbon and oxygen, and as it cools, some of the carbon could crystallize into huge diamonds, maybe hundreds of meters across. Could be good if you want to get engaged, I guess, but it might be a bit heavy to carry around. The sun is big. As I said, 1,000,000 Earths can fit inside the sun. Some stars are much bigger than the sun. 1 billion suns would fit inside Betelgeuse. You can see on the picture here, that's Betelgeuse. I'm just going to put my glasses back on so I can see my screen. That's Betelgeuse there. The sun is a bit under 1 pixel, just right in the middle there. If Betelgeuse was, the centre of Betelgeuse was where the sun is, Jupiter would be inside Betelgeuse. It's a huge star. Betelgeuse is the 10th brightest star in the sky. It's the 2nd brightest star in the constellation Orion. Orion is one of those constellations that is very easy to pick. Who's actually ever spotted Orion in the sky? I'm sure quite a few people have. Yeah, it's very distinctive in having 4 bright stars in a sort of a rectangle, and 3 stars in the middle, which are very similar in brightness, equally spaced in a straight line, which is very distinctive in the sky. So that's very easy to pick up. The Romans, that we get most of our constellation names from, called the constellation Orion, and you can see the picture that they interpreted down in the left corner there, where Betelgeuse, the red star, and Bellatrix, the other star at the top, are the shoulders, and there's two stars, Rigel and Saiph, at the bottom, which are the knees. And the 3 stars in the middle are the belt, the belt of Orion. Now, Betelgeuse is red, and obviously, it's a red giant, and it's obviously red when you look at it. It's tempting to think that it's called Betelgeuse because the juice that comes out of beetles when you squeeze them is red. But it's not. It comes from the Arabic Betelgeuse, which is the giant shoulder. The Arabs had the same constellation, but they called it the giant rather than Orion. And we get the names of a lot of our stars from Arabic, because they named the stars in about the 9th century or so. And we've kept those names, which is why a lot of stars have funny names, like Zubin al-Janubi is the brightest star in Libra. Betelgeuse is 16 times the mass of the sun, so it's quite a bit bigger than the sun. Stars that heavy don't become white dwarfs. They die more dramatically in supernova explosions, shining 1 trillion times brighter than the sun for a few days. So that's brighter than every one of the 400 billion stars in our galaxy all put together. And that goes for about a month generally.
Are we going to see one of those soon?
We might, as we'll see in the I think in the next slide. Yeah. There were 4 visible supernovas in the Milky Way in the last millennium. They're not very common. We've had 4 in 1,000 years. One in Lupus, one in Taurus, one in Cassiopeia, and one in Ophiuchus. We haven't had one since 1604, so you might say we're due for another one. The 1006 supernova was 15 times brighter than Venus at its brightest, and would have been easily visible during the day. Now, those magnitudes on the right, they're the brightness, and it's sort of a bit counterintuitive, but for negative magnitudes, the bigger the negative number, the brighter they are. The reason for that is that magnitudes started when people first decided to classify stars as first magnitude, second magnitude, first magnitude being the bright ones, down to 6th magnitude being the ones that you could only just see. And later on we put numbers to that, we called 1, 2, 3, 4, 5 and 6, so of course the smaller numbers were the brightest stars. Now stars brighter than magnitude 1 became magnitude 0, then negative 1, and so on. Venus at its brightest is magnitude negative 4. The same as the Cassiopeia supernova, but not nearly as bright as the Lupus one. That was 15 times as bright as Venus. When Betelgeuse goes supernova, it's being just 600 light years away, which is very close. None of those were that close. It will be over 1,000 times brighter than Venus. At magnitude minus 12, it will be as bright as the full moon. And of course, the full moon, the light is spread out over quite a large area. With the supernova, it will be just basically one pinpoint in the sky, with producing as much light as the full moon does now. So it'll be quite spectacular. And the thing is, Betelgeuse is due to go supernova any day now. So we might in our lifetimes be treated to an astronomical spectacle. Of course, when astronomers say any day now, they mean any day in the next million years. So it might not, but you never know. We keep our fingers crossed. Okay, what causes a supernova? I've talked about supernovas. The sun gets its energy by fusing hydrogen to helium. And it fuses 600 million tons of hydrogen to 596 million tons of helium every second. And most of the rest is turned into energy as gamma rays and some neutrinos. When it becomes a red giant, it will fuse helium to carbon and oxygen. Now, just to explain, a hydrogen atom is in the sun. The atoms the atoms are broken up into their nucleus and their electron. They're completely separate. The hydrogen nucleus is just one proton, and its electron is floating around somewhere, not with it. Now, the fusion of hydrogen to helium basically involves 4 of those protons getting together, 2 of them combining with electrons to turn into neutrons, and then you have a helium nucleus, which is 2 protons and 2 neutrons. Now, if you combine 2 of those together, you then get a beryllium nucleus, and add another one, you get a carbon nucleus. Add one more, you get an oxygen nucleus. And that's as far as the fusion reaction goes in a star like the Sun. Okay. So when it comes to a giant, it fuses helium to carbon and oxygen. Then it will throw off its outer layers in a series of explosions, and the remaining core becomes a white dwarf. In stars like Betelgeuse, the pressure and temperature are high enough because there's a lot more mass pushing in through gravity for the carbon and oxygen to then fuse further. They absorb more helium atoms, and they can turn into neon, magnesium, silicon, and finally iron. And each step releases energy until the whole core is made of iron. But of course, it's not metal iron, it's sort of very much a plasma. Fusing iron doesn't release energy, so the core then cools down until it no longer has enough pressure to hold up the weight of the outer layers. Then it collapses from 20,000 kilometres wide to 20 kilometres wide in less than a second. So a supernova is a very sudden event. The outer layers fall onto it at a quarter of the speed of light. Then they rebound into space, producing the supernova explosion. And you might think, that when the outer part of the star collapses onto the core, which is now just 20 kilometres in diameter. Is this working okay? Yeah. You might think it might bounce back to about the same size, but what happens also is that as the core collapses, it emits a huge number of neutrinos. And those neutrinos give an extra kick to the outer part of the star and make it explode into space, which makes it into a big explosion and exposes the core of or the inner part of the star, which is a fantastic temperature. It's like about 1 billion degrees centigrade, and that produces all the light that we see. Now, I mentioned neutrinos. The sun produces neutrinos as it fuses hydrogen to helium. One of the things that wasn't in that diagram before, but one of the products is a neutrino. A neutrino is a very light subatomic particle, much lighter than an electron, and they generally travel very close to the speed of light, like about 99.9999% of the speed of light. Every time that four hydrogen atoms combine to make a helium atom in the sun, there's, I think, about 2 or 3 neutrinos are ejected. And they travel out through the sun, and across the universe, and a lot of them will hit us, and they'll go in one side and straight out the other. In fact, every second, every one of you has about 100 trillion neutrinos from the sun passing through your body, but you don't notice it. They don't interact with your particles very much at all. In fact, the vast majority of them will go right through the Earth without being affected by it. They're very difficult things to detect. Occasionally, though, they do interact with things, which is why we've got neutrino detectors which can pick them up, because very occasionally they will react with things. One of the way actually that we first spot a new supernova on Earth is not from the light, because the light takes a little while to develop, because the outer part of the star has got to expand away, but it's from a burst of neutrinos. If we get a sudden burst of neutrinos, we know that a supernova has occurred in one of our neutrino detectors, and then we can focus our telescopes on that, and then we can see the supernova take place. Okay. So, the outer part of the star is thrown off into space. The core is left as a neutron star made of solid neutrons. Now, as you know, an atom is a tiny nucleus with a big cloud of electrons around it. The nucleus is protons and neutrons, and the cloud of electrons is about usually about 100,000 times as wide as the nucleus. Now, what happens in a supernova is when the star collapses under the huge gravitational force, the electrons are pushed into the protons in the nucleus to form neutrons. So electron is negatively charged, proton is positively charged, put them together and you get a neutron with zero charge. So all of the protons in the nucleus suddenly become neutrons and the electron cloud disappears. And so you've just got neutrons, which then, it's the electron clouds that keep the atoms separate in most of matter. And so sort of the electrons repel each other, being negative in one atom and negative in the other. But once they're all inside the nucleus, that repulsion doesn't happen anymore. And so the neutrons then can snuggle right up to each other, and they get closely packed very much more densely than they were as whole atoms. And that is why the core of the star can collapse from 20,000 kilometres wide to 20 kilometres wide. Obviously the core, as a neutron star, is going to be very dense. 1 teaspoonful of a neutron star. Remember, a white dwarf, 1 teaspoon weighs 5 tons. For a neutron star, 1 teaspoonful weighs 1 billion tons. Gravity on the surface is 200 billion times stronger than on Earth. If you dropped a spanner from waist height, it would hit the ground at 7 million kilometres per hour. Not that you could, because you would be instantly squashed down to a thin smear on the surface of the star. Like that. I'm going to finish, I'm getting fairly close to the end here. I'll ask for questions at the end if anybody wants to ask any of those two. We don't have any questions, so I'm going fairly fast. Ballerinas spin faster when they pull their arms in. You've all seen pictures of that. In the same way, when a star gets compressed down into a neutron star, it spins faster. Many neutron stars can spin more than 500 times per second. So imagine something 20 kilometres in diameter going around 500 times a second. It's quite incredible. Ballerinas can't do that. Stars more than 25 times the mass of the sun, when they go supernova, instead of a neutron star, they produce a black hole, which is so dense that its gravity stops even light from leaving its surface. So a black hole looks something like that. As you might have seen pictures of black holes recently. Who's seen the pictures of the black holes that they produced, the white gas? Some people have. And they don't look black like that. They're sort of, they're usually shown as sort of red and orange and a sort of a bit of a ball with a bit of a sort of ring going around it. What you're actually looking at there is not the black hole, it is the stuff that is falling into the black hole and spinning around it. And being electrically charged, as it's accelerated, it emits electromagnetic radiation as light. So it's the stuff around the black hole that you can see. The black hole is just black. You can't see anything there. Okay, if you fell into a black hole, that would be the end. Alright, so I've got a bit of time for if anybody's got any other questions. I've got a bit more time here, or we can have an early mark, whichever. Oh, I've had enough, yeah. Okay.
So anybody want to ask a question?
Just about the methane, the question of methane, which is everybody's talking about at the moment. So in the beginning there, you're talking about the oxygen and methane. So is methane really a bad thing to have on Earth at the moment?
At the moment, we up until fairly recently, we had negligible methane in the atmosphere. The methane itself is only a very small part of the atmosphere, maybe 1 part per million or something like that. It's still fairly negligible. It doesn't do us any harm directly, but it does have a greenhouse effect, and it is adding to the effect of the carbon dioxide. So in that sense, it's making the global warming worse than it would be without it. And methane at the moment is mostly coming from thawing of frozen soil in the Arctic. Because a lot of decaying matter in that soil has been frozen, but now that it's unfreezing, it's releasing methane, and that methane is getting into the atmosphere. So some is from cows. Yeah, that's a good point. Cows do produce methane as well. They burp up methane, and yeah, I was forgetting about that. And that's a sort of an important contribution as well. I know that more recently the focus has been on the Arctic source, because that's just sort of something that's happened fairly recently. Cows have been around for a long time, but we do have more cows than we have had in the past, and so they are a contribution as well. Methane eventually in the atmosphere gets converted back to carbon dioxide, reacts with the oxygen, but it takes, it's got a half-life of about 30 years or something like that, so it stays there for quite a while, warming up the atmosphere before it disappears.
Anybody else? Yes?
The Andromeda Galaxy is the furthest thing that humans can see with the naked eye.
True.
Actually, how far away is it?
It's 2 million light years.
And what does that consider in, say, kilometres?
Kilometres. 1 light year is 10 to the power of 13 kilometres, or 1 with 13 zeros after it. So 10 trillion kilometres is 1 light year, and the Andromeda Galaxy is 2 million light years. The universe is a big place. The farthest things we can see with the telescope are about 13, no actually in their present position they are about 40 billion light years away. From the light we're seeing now, came from them when they were more like about 13 billion years away, but of course the universe is expanding, and since they emitted that light they've moved a lot further away and now are about 40 billion light years away.
In your opinion, is the climatic problem we are supposed to be having today as serious as they make out?
People have different opinions on this, and I can't say that I know that, any better than other people, but I do feel that it is a fairly serious problem. It's the global warming is very definite, that's undeniable. What people argue about is what's caused it, whether it's natural or whether it's caused by carbon dioxide going into the air. From an a priori perspective, we know that putting more carbon dioxide into the air increases the greenhouse effect, which would increase global temperatures. So to some extent, it's got to be man-made. As I said there earlier on, catastrophes aren't always bad in the long run. Maybe for whatever's living on the Earth in another million or a billion years, they might think, oh, that was. I'm very glad that happened because we wouldn't have been around here otherwise. But for the people who are here now, not so much maybe us, but 2 or 3 generations down the track, I fear that it might cause sort of fairly serious problems.
Thank you.
Do they know how fast the billions of galaxies are expanding?
When we get to the edge of the observable universe, the galaxies there are expanding, are moving away from us at the speed of light. And anything beyond that is moving away faster than the speed of light, so light will never get to us from them and we can't see those. Now, Einstein said that you can't move faster than the speed of light, which is true, but that means that you cannot move through local space faster than the speed of light. But space can expand such that this bit of space is moving away from that bit of space faster than the speed of light. And in fact, the edge of the observable universe isn't the edge of the universe. There's no reason why galaxies should stop there. They will continue. There's good evidence to suggest that the real total universe is at least about a few billion times as big as the observable universe, and so things will be moving away from us at much faster than the speed of light. It may well be infinite. We don't know.
Yeah, I know there's somebody over there that wanted to ask a question. The black hole, is that actually a star that you just can't see? I was just trying to work that out when you were talking about it. And understand it.
Yeah, the core of the star, when a supernova occurs on a massive star more than 25 times the mass of the Sun, in the same way the core collapses, the outer layers are thrown off, but the gravitational effect, the gravity on the surface of the core then is sufficient for it to hold light back, and light cannot escape from it. So it's still the core of the star, but it becomes then inaccessible to us in that we can't see it. It's still there, we just can't see it. It still has the same gravitational effect. A black hole will have the same gravitational effect as a star. And in fact, planets can theoretically still orbit black holes. And I think there are binary stars, where there are 2 stars. One has turned into a black hole, and the other one is going around it. And you see a star going around what looks like nothing. And so it's still there. Strange things actually happen in black holes because Einstein's theory of general relativity says that as you go into a very large gravitational field, time slows down. So if you saw me fall into a black hole, you would see me accelerate towards the black hole, but then slow down. The surface of the black hole where you can't see anything beyond is called the event horizon. As I approach the event horizon, I would tend to slow down. You would see me slowing down. And eventually, if you could wait long enough, I would stop at the event horizon because for me, time stops there. But, sorry, for you, looking in, time stops there. But for me, time doesn't stop, time carries on, and I will go straight through the event horizon, right to the centre of the black hole, where everything in that black hole is in one point called a singularity. And of course, you don't survive that. But that by the time you get there, the outside universe would be infinitely old, because time has continued there, but it's stopped for you. It's all a bit strange.
There was a chart over between the South Pole and the southwest part of New Zealand, a black hole, which I don't know the same thing as what you're
And nobody else can hear your question.
smaller.
Including David.
A black hole between the South Pole and New Zealand.
Yeah, yeah.
I think that'd be a different kind of black hole, because if there was one there, I think we'd all have been sucked into it long ago.
Sorry, this is in the sky.
Oh, there's the ozone, the hole in the ozone layer.
Yes.
Yeah, that's a different thing from a black hole. And that's caused by chlorofluorocarbons mainly that we put into the atmosphere, and it's reacted with the ozone, particularly over the poles, particularly over the South Pole. So,
And they just class it as a black hole.
oh, yeah, I guess you can call it black. It's a totally different thing from an astronomical black hole, though. Yeah.
I see that just found another